In the previous video, you learned about some terminologies in graph theory. Now for this video, you will learn how to illustrate or how to get the shortest path from one vertex to another given a graph. We call the process of shortest path as Dijkstra's algorithm. To apply the Dijkstra's algorithm, there should be a connected, weighted, simple graph G and a starting vertex. Now, this algorithm solves only the problems with non-negative costs. Remember, the edges of the graph G are labeled with numerical weights, so the numerical weights must be non-negative. Now, this algorithm is used to find directions between physical locations such as driving directions, and it is used to solve minimum path delay in networking or telecommunication applications and many more. The Dijkstra's algorithm begins by assigning initial or starting values for the distances from the starting vertex S to every other vertex in the given graph. It operates in steps, where at each step, the algorithm improves the distance value. So when we say improve the distance values, as long as we get a distance that is shorter than the previous one, then that means that we're improving the distances values. Now at each step, the shortest distance from the vertex S to another vertex is determined. In this algorithm, each vertex has a state. The state includes the distance value of the vertex from the starting vertex and the status label. Now, the distance value of a vertex is the number representing an estimate of its distance from the starting vertex. The status label is an attribute specifying whether the distance value of a vertex is equal to the shortest distance from vertex S. The status labels could be permanent or temporary. If the status label is permanent, then it means that the distance value is already equal to the shortest distance from the starting vertex S. Otherwise, the status label of a vertex is temporary, which means that we can still, or it is possible, or still possible to find a shorter distance than the previous one. Now, the algorithm maintains and updates the states of the vertices, and at each step, one vertex is designated as the current vertex. Let us illustrate the Dijkstra's algorithm. Let us find the shortest path from the starting vertex S to all the other vertices of the given graph on your screens. Let's begin by labeling the starting vertex S by 0, P. This means that 0 is the distance value of S from itself, and its distance is already permanent because we know that the distance of S to itself will always be 0. Next, we label all the other vertices by infinity, T. The infinity is used because later on in the algorithm, if a distance value will be compared to infinity, that distance value will always be less than infinity. And then the status label is T, which means temporary. It is because that we can still find a shorter distance compared to infinity. Since the status label of the starting vertex S is permanent, we designate the starting vertex S as the current vertex. So we color it by green. Since S is our current vertex, we add its distance value to 14 because S is adjacent to A and A is labeled temporary. Now the sum of 0 and 14 is 14, which is less than infinity. So we must replace this by 14. Now we also do this for the second edge here. Now because S is adjacent to E and E is labeled temporary, we add 0 and 9 And then we get a sum of 9, which is less than infinity. So 9 will replace infinity. And then also, since S is adjacent to F, and F is labeled temporary, we add 0 and 7. So the sum would be 7, and that would replace infinity. And then we get the following. Now, among the vertices labeled with temporary, we compare their distance values. The one with the lowest distance value will now be changed with a permanent status label. So in this case, comparing 14, infinity, 9, infinity, and 7, the one with the lowest distance value is 7, which belongs to vertex F. So that means the temporary status of vertex F will now be changed to a permanent status. So this means that the shortest distance from S going to F is equal to 7. Now, since the status of vertex F is changed from temporary to permanent, then we say now that the vertex F will be our new current vertex. Since the vertex F is our new current vertex, we change its color to green, while the starting vertex S color will be changed to red, which indicates that it cannot become a current vertex anymore in the succeeding steps. Now, since vertex E is adjacent to vertex F, and the vertex E is labeled temporary, we add 7 and 10 and compare it to 9. Now, 7 plus 10 is 17, but 17 is higher than 9. So, which means 17 cannot replace 9. Now, also, the vertex C is labeled temporary, and the vertex C is adjacent to F. So, we add 7 and 15 and compare it with infinity. So 7 plus 15 is 22, which is less than infinity. So we must replace infinity by 22. Now, since S is also adjacent to vertex F, we cannot update it anymore because S is already labeled with permanent. Among the vertices E and C, only the distance value of the vertex C is updated. Now, after updating, we must compare all the distance values from the temporary labeled vertices. Now, in this case, the one with the lowest distance value among the temporary labeled vertices is 9, and it belongs to E. So this means that the status label of the vertex E should be changed from temporary to permanent. In this case, we already found that the shortest distance from the starting vertex S going to the vertex E is equal to 9. Now, since the status label of the vertex E is changed from temporary to permanent, we will now designate E as our new current vertex. Since the vertex E is our new current vertex, we change its color to green, while the color of the vertex F will now be changed to red, which means that F cannot become a current vertex anymore in the succeeding steps. Now we update the temporary labeled vertices which are adjacent to E, and these are vertex A and vertex C. So to update, let's add 9 with 2. So 9 plus 2 is 11, and compare it to 14. Since 11 is less than 14, we replace 14 by 11. Now for the vertex C, adding 9 with 11 will give us 20. And comparing it with 22, 20 is less than 22. So we must replace this by 20. After updating, we see that the distance values of the vertices labeled with temporary are 11, infinity, and 20. The one with the lowest distance value is vertex A, and it has a distance value of 11. So this means that we're going to change the status label of vertex A from temporary to permanent. So this indicates that we already found the shortest distance from the starting vertex S going to the vertex A, and this is given by 11. Since the status label of vertex A is changed from temporary to permanent, this means that A will now become our new current vertex. That means the color of vertex A will be changed to green, while the color of vertex E will now be changed to red, which means that vertex E cannot become a current vertex in the succeeding steps. Now let's update the distance values of the temporary labeled vertices which are adjacent to the current vertex A. So that is the vertex B. So to update, we add 11 with 9, which is 20, and comparing it to infinity, 20 is less than infinity, so we must replace this by 20. Again, after updating, we inspect the distance values of the temporary labeled vertices. In this case, we have the distance value 20 for the vertex B and the distance value 20 for the vertex C. In the previous steps, we find the one with the lowest distance value. But since there is a tie in the lowest distance value, now we choose any of the two vertices B and C. In this case, let's choose the vertex B. Here, we change the label of B from temporary to permanent, and this means that we already found the shortest distance from the starting vertex S to the vertex B, and this is given by 20. Since the status label of B is changed from temporary to permanent, this means that the vertex B will be our new current vertex. Since vertex B is our new current vertex, we change its color to green, and the color of vertex A will be changed to red, which means that A cannot become a current vertex in the succeeding steps. We are going to update all the temporary labeled vertices that are adjacent to B, but in this case, it's only C that is labeled temporary that is adjacent to the vertex B. So let's try to update its distance value. So to update, we add 20 and 6 and compare it to 20. But 20 plus 6 is 26, which is higher than 20. So in this case, the distance value of C will be retained to 20. Now, since it's the only temporary labeled vertex, we change this label of C from temporary to permanent. So this means that we have found the shortest distance from the starting vertex S going to the vertex C, and it is given by 20. Now, since the status label of the vertex C is changed from temporary to permanent, then we say that the vertex C is now our new current vertex. Since the vertex C is our new current vertex, we change its color to green, while the color of vertex B will now be changed to red. However, since all the vertices now have status label permanent, that means that the algorithm terminates. This means that all the vertices will now be colored red, and now we have solved the shortest distance from the starting vertex S going to all the other vertices in the graph. So this means that the shortest distance from vertex S going to vertex A is 11. The shortest distance from vertex S going to vertex E is 9. The shortest distance from the vertex S to the vertex F is 7. The shortest distance from the vertex S to B is 20. And the shortest distance from the vertex S going to the vertex C is 20. Now this ends our discussion about graph theory and finding the shortest path. Now for your exercise, you can try this by finding the least expensive route from vertex I going to vertex L given the following graph.